Let's take a look at the feedback circuits. This is negative feedback. We have XS and YS. The feed-forward transfer function HS, that is called the open loop transfer function. If you disconnect the feedback, you will see the transfer function from X to Y through this HS. So that's why we call it open loop transfer function. Now the Y over X is the closed loop transfer function, and the gain around inside this loop, G times H, is called the loop gain. So you have to be familiar with all the terms we are talking about here. Let's derive the transfer function out of this. Let's say if this output and X input, then the input of the GS block would be Y, and then output will be G times Y, right? So at the input we have X minus G times Y. That would be amplified, right? So the overall equation would be X minus GY times HS. If you summarize this equation 1, then you will get this kind of a very important characteristic. Here at the top we have H of S. At the denominator we have a 1 plus G times H of S, right? So this part is called the loop gain. This part is called open loop gain. And this part is called, right, closed loop transfer function. So this kind of a negative feedback is very essential in precision analog circuit or digital or signal processing. We had took the subtraction there at the input. If you make it positive, then it becomes positive feedback. So in the positive feedback, we will see later, the output will not be stable. So it mostly used in the oscillator or digital latches. So this kind of things used in that. So one of the thing that we already have seen is that one of the differential load has the cross-coupled pair like this. This is a typical positive feedback. Why? Because let's say if the drain voltage on one side is go up, then the current increase on the right the transistor, so the output drain will go down. If this goes down, then the gate voltage of the left transistor goes down. So what happened? The drain voltage even go up higher, right? So this is the positive feedback. It will grow the amplitude, and then the other side also go down even lower like this, going up and down, right? So it will stop amplifying signal until it hits the limit, like supply and ground, right? Let's take a look at the signals inside the negative feedback. Let's assume that if we have the sinusoid waveform at the input, then the H of S will have there's some, so input and output with a certain relationship. Let's say H of S is a certain gain, a large gain in there. So small error is like let's say typically in OPM application we design that the, let's say this is, let's say, infinity of gain and close to infinity, let's say, then GS, let's say, time kind of half the loss, right? Let's say it becomes like this and that. And what happens is that once the signal, let's say, if the signal go up, the output of the adder will tend to go up, right? And then H of S, it will like make it very large increase, and then only the fraction of the output will go come out through the GS, and then subtract it. So this amount of increase and that one, it will not match initially, but since we have infinity very large gain at the H of S, the only way, so it will settle to the constant value is that the error approach to zero in a way, so that this feedback signal and apply the reference input amount is the same. In that case, error approach to zero. Now the 0 times through the by the limit theory, so error times H of S, right? Limit error approach to zero, that becomes a constant value. Right? This is 0, so right. So this is, so once that is error approach to zero, then output becomes constant. So if you write a transfer function here, overall loop transfer function, closed loop transfer function is 1 plus H of S, 1 plus G times H of S, right? Let's say H of S again is A and 1 plus half of the A. Once the limit making A goes to infinity, the what? The overall gain would be what? Equal to 2. The constant gain is observed. So our signal just amplified by 2x through this, right? This is something that we had learned in the undergraduate courses, right? So let me list up the property of the negative feedbacks. This is very important. You must memorize and understand those characteristics. The first is gain desensitization, and second is terminal impedance modification and bandwidth modification, nonlinearity reduction, and noise suppression. All these can be achieved by the negative feedback. This is very important. You must understand this. Throughout this course, we will see that one by one. Okay. So the typical negative feedback construction is like this. For feed forward gain is A, so A over 1 plus beta A is a closed loop transfer function. If the A is large enough, let's say if A times beta approach to infinity, right, very large, then what happens? So beta is between 0 to 1, right? And then overall equation would be similar like this, right? If you know that you are using this factor, the 1 plus x, and if the x is small, right? If the, for this equation, if the x is small, approach to 0, and it becomes like a approximated 1 minus x, right? So we use this property. So for this equation, we divide things, this equation, by a beta, then what? So a divided by a beta, 1 plus a beta plus 1, right? So this portion becomes 1 over beta, right? And the denominator, we have this equation, right? This relationship. Since a beta is very large, 1 over beta, this term, we can make this term approximated like that. So as you can see, if the a beta loop gain is large, the overall gain will be approached to 1 over beta, but the small error determined by the 1 over beta, right? So if the large loop gain there, it will be 1 over beta. So a beta, it becomes infinity like this. So if our desired gain is 1 over beta, then the term on the right, 1 over a beta, would be the gain error term, error terms, right? Its gain error term will be going down only if a beta loop gain is large. So the gain error goes down if the loop gain a beta, this fact is that this means that you have to remember that the feedback, negative feedback, the property of the feedback, or the strength of the feedback, is measured by what? Loop gain. Loop gain a beta. So whenever you evaluate your negative feedback, you must understand and investigate how large your loop gain, right? If the loop gain is very large, then it behaves like a more ideal. What is ideal? The gain is just defined by the inverse of the feedback factor of 1 over beta, right? Let's take a look at the gain desensitization first. For the common source amplifier, open loop gain is GM times RO here, minus, if you take the polarity correct. And for this amplifier, gain is like this, but if you have some kind of feedback, like the capacitive feedback shown in here, so we just assume that all the bias is properly done. So obviously the capacitive input here will not properly set the DC voltage, but we are just assuming that there is a very large gain bias resistor, very large one, and then current source bias and something like that. So it generates the VGS properly here. So this is the open, very large resistor, bias resistor, so this you can just ignore that for our analysis. So for this kind of feedback, capacitive feedback analysis, so you can take it like the impedance equation, 1 over SC1, like that. So the how we calculate, so we have R1 RO here. Let's say take it the simplest way would be not see it may some involve some mathematics. So to do that, so I'm gonna do like this. So here V out, here we have the current through the RO would be what? V out over RO, right? And then we have to sorry about that. So we have to identify all the current through the transistor and resistor. So output, fraction of output voltage will be appear here on the Vx node, and that will create the transistor current there, right? So we can find out that. So V in and V out. So Vx node first, Vx equal what? V out minus V in over, we have impedance division, right? So we have a resistor divider there, the impedance divider. So how we calculate? So 1 over SC1 times 1 over SC2 plus, and what? 1 over SC1. That would be the Vx node voltage. So V out minus V in times what? C1 plus C2 C2, right? Once we identify that the current through M1, let's say ID, we have ID, that ID would be what? Would be GM times Vx. So we know the current on the output node, so current through the RO here, current through the transistor here, and current through the feedback there. It's quite looks like a complicated initially. So we have to take all the current sum equal to 0. So such current must be in terms of a V in and V out. So we have to specify the current through this part, right? So this current through that part will be what? This current will flow to the input. So the, let's say IX, IC, what is that? The current through the C1 and C2 would be what? V out minus V in over impedance. What is impedance? The C1 and C2 in parallel. So 1 over S C1 and C2 in parallel. So what? C1. So C equivalent, let's say C equivalent is what? C1 plus C2, C1, C2, right? Now that the plus ID, so ID plus RO over V out would be 0, right? So the ID we have here. So rewriting equation 1 would be minus V in times SC equivalent plus GM times V out minus V in C equivalent, right? We have a this is equation 1 and this is equation 2 from 2, and finally plus V out over RO equal to 0, right? So this equation now, everything is in terms of V out and V in. So you can get the summarize, rewrite the equation, then you will get this equation, right? Another characteristic of the negative feedback is that it changes the terminal impedance. For example, if you have a negative feedback through the C1 and C2 in this circuits, this is a common sorry, this is the common if this is the input gate bottom, this is the common source amplifier with the cascaded. But if you take the input from the V in, that it becomes what common gate amplifier, right? This signal goes into the source, and the gate is at the DC VB. So this is a common base amplifier, CM base. As common source common gate amplifier, CG amp. So the feedback going through the M2. In this case, the input impedance would be what? Without this C1 and C2, if you disconnect that feedback, then you will see just the impedance through the M1. That would be 1 over GM1 plus GMB, considering the backgate effect, right? Because the source node is also moving. So for the body, when the body is tied to ground, the body voltage and source voltage will be also changes, right? So VBS is also changing. So we have the transconductance. But if you close the loop by C1 and C2 feedback, here the beta is the feedback factor is from, so feedback, so beta is what? 1 over SOC1 plus 1 over SOC2. So denominator it like this, and the numerator we will have what? Numerator 1 over SOC2, right? So this will be C1 plus C2 and C1, right? So this is the feedback factor. So if you calculate the overall impedance through that, so we apply the test voltage Vx and measure the test current Ix, then you will get the relationship between Vx and Vix, right? That would be, if you calculate that, you get the additional term 1 over 1 plus GM2 RD times the C1 over C1 plus C2. So as you can see, the original input impedance is changed by this amount of factor. So that actually changes the impedance. I will leave the calculation, detailed calculation or derivation for your the work for your exercise. So this is something that you can have out of the negative feedback. This is another example. You can find the Rin closed impedance through this the register feedback RF there. So input to output, there is a connection through the RF. So in this case, if you find the closed loop input impedance, that would be RF divided by 1 plus GMRD. But if you the R how about the R out? So R out is also closed one. It's found by RD over 1 plus GMRD. So as you can see, so it is the different the input and output impedance, right? So in both case, by the first case, you have the RF. You look at it as some kind of the Miller gain. So gain from here to there, right, is GMRD. So RF impedance is reduced by 1 plus loop gain, 1 plus GMRD, 1 plus GMRD. So you know that by the Miller effect, GF there, if the gain from here to there is the AV, in this case minus GM RD, so the feedback RF impedance looking in would be like this, right? So for simple derivation, I'm gonna just drive for the first input closed loop response here. Let's say this is we need some so overall G in equivalent is GF times 1 minus AV, right? So this would be RF 1 plus GM RD, right? You can drive through the exact equation by, let's say this is Vx and measure the Ix. If this is Vx, the output would be what? Minus GM RD times Vx. Since the current through the RF would be what? Ix would be voltage difference between Vx is minus GM RD divided by impedance, which is RF, right? So the Ix to Vx relationship from 1, we can find that minus GMRD times Vx, right? Vx is there. So the relationship G in equivalent will be Vx over Ix. Vx is the RF over 1 plus GM RD, right? So you can do the similar derivation on the output closed loop impedance, right, by applying the test voltage and find out the test current relationship between the voltage and current. Okay. For output impedance, equivalent impedance, you can have some kind of insight. If you have some insight, it can be easily calculated. So we have RD in parallel with this guy. For input is open because this is we consider that I in case is equal to 0. In that case, the current source impedance is infinitive. So we have a impedance RD in parallel with the bottom circuit network impedance. As you can see, the voltage here and gate is the same because there's no current through the RF because the input gate impedance is infinity, right? So there's no current flow through the RF. So this voltage and that voltage is same, so it is exactly same as just diode connection. So we have the RD at the top in parallel with the bottom 1 over GM. So this is the output impedance. So without RF feedback resistor, we would see the output impedance RD, but with the RF feedback, the output overall impedance would be 1 over GM in parallel with the RD. Okay. One of the impedance transformation by the feedback example, the application is fiber optics. So there's a photodiode here, D1. Whenever it receives the current changes, so output is current variation. So it looks like the what? So equivalent to current source there. So whenever it receives the light, the change in DC current would be the output. But the amount of voltage variation is so small rather than so the output is the in current rather than the voltage. So its output impedance is very large in diode, in reverse bias the diode. So the output current level is the variation is must be sensed by some kind of amplifier. But in order to observe this current variation need to be somehow flow through the R1 so that this current variation will change the voltage, let's say ID times R1, right? But the problem with this kind of the structure is that whenever you load some kind of impedance or right impedance on the right, so each output voltage will changes, right? But without such kind of so this kind of a passive network characteristic very dependent on the output load condition. So passive network passive circuit is sensitive to load condition, right? So in order to avoid such load sensitivity to load condition, we use negative amplifier like a transimpedance amplifier. So by having this negative feedback, this input becomes the AC ground. So the low impedance. So low impedance. So whenever ID change, the current changes, the amount of variation will go through the negative feedback here. It will create the voltage drop, right? ID times R1. So let's say make it small signal current change. Let's say so IAD times R1. If the input is current, equal this ID, in order for this ID to flow through the R1, we have to have a low impedance on the right hand side. So equivalent impedance looking into amplifier must be small, because if this impedance is large, the amount of current will flow through the CD1. For example, on the left hand side, the current variation on the ID may affect, it will create voltage change. This ID will the part of the ID will flow through the capacitor, and the part of that the current will flow through the R1. The output impedance, output voltage will be large only if that most of the ID current flows through the R1. Then it becomes the max gain and max signal voltage it will get. But if you have a large CD1, like a large capacitor there, the output voltage will be ID times what? R1 in parallel with the 1 over SCD1. So if the large C1, large capacitor is there, then overall output voltage change will be very small because the low impedance by the capacitor. To avoid such kind of a problem, so we can have the negative feedback amplifier so that the input impedance looking into amplifier G equivalent. So G equivalent is much smaller than 1 over SCD1. Then the older current will flow through R1 that will create the large voltage drop. So on the left hand side it was I times R in 1 parallel with the 1 over SCD1. On the right hand side the older change will be set by the R1. So ID times R1 would be the output response regardless of the CD1. So as you looked at in the previous example, so GEQ is what? So R1 divided by 1 plus A. So input impedance looking into the amplifier is lowered by this negative feedback, right? So this is called the trans impedance amplifier. It is lowering input impedance. So this trans impedance amplifier is suitable for what? If the input is current input, like a photodiode. The photodiode is the current input. So the current source input has the characteristic as large output impedance, right? So that the input signal is rather than voltage, it is current rather than the voltage. Okay. Another characteristic of the negative feedback is the bandwidth expansion. For example, for the forward gain AS, its bandwidth is omega 0, which is limited by that. In that case, use the passive feedback gain as the beta, then use this network and then try to solve the input to output response. That will what? So overall gain would be y over x equal to forward gain A over S over 1 plus AS times beta. So we plugged in the AS with the left hand side equation, then you will get this equation. So you try to simplify that, the overall response like that. As you can see, the passband gain is reduced by the 1 plus A beta, A0 beta. And also bandwidth now here is the original bandwidth is expanded by the 1 plus A0 beta. So the gain N is reduced by 1 plus A0 beta. The bandwidth is expanded by, increased by by 1 plus A0 beta, right? So let's see this characteristic in the frequency response in the next slide. As you can see on the bottom, original amplifier for the gain, its gain, DC gain is the A0, and the bandwidth is only limited to beta 0. Now, after the feedback, your DC gain becomes like this. If the A0 is large enough, then it approaches to 1 over beta. So beta is here is less than 1. So 0 is the obvious. If the beta is 0, then there's no feedback. So if this is the case, then 1 over beta is greater than 1, right? Greater than equal to 1. So now the bandwidth is 1 plus A0 beta times omega 0. So the bandwidth is expanded, right? As you can see, the below this certain point is the flat gain, but after that point is it just follows the original amplifier characteristic, meaning within this frequency range, negative feedback, right? Negative feedback, I mean, does something. So negative feedback effect only valid up to this point. So the what? Like that. In the previous slides, I have talked about this. During this in this region, negative feedback is that becomes the effective. So as I talked earlier, the strength of the negative feedback is measured by what? The strength of negative feedback is measured by loop gain, right? The loop gain is what? LG is A0A times beta. So as long as the loop gain is greater than 1 or much larger than 1, then the negative feedback becomes effective. Let's plot this loop gain here, so over frequency, so loop gain, so AS times beta. Now, since the AS is defined by like this, right? So it will be similar, but the beta is constant below or less than 1. So it will be like this equation. So AS times beta. So as you can see, this is log plot. The negative feedback becomes effective around there, right? So beta, so originally was like this, right? Originally like this, and beta will like this. So I'm gonna draw like this, and then originally, so that one was what? That one was A of S, and then this one, the lower graph will be what? AS times beta. So the AS times A beta will be the shift gain will be shifted by the beta, right? Now as you can see here, so original amplifier bandwidth was what? A and omega here. So that one, if this is omega 0, then this original amplifier, the unity gain frequency would be what? A0 DC gain times what? The omega 0. This is the gain bandwidth product, right? This is approximately FU, right? A0 times omega 0. So for the similar method, we can estimate the frequency where the loop gain is equal to 1. That would be what? The DC gain times A0 beta. The DC gain will be what? Now go down by beta. So A0 times beta, right? This is the loop gain, and then omega 0, right? So approximately the feedback, it becomes effective up to this point. This is frequency. That frequency is similar to 1 plus beta A0 omega 0, right? It's very similar frequency. So as long as the loop gain, the strength of the feedback edge becomes effective in this region, your feedback characteristic, overall feedback characteristic, overall closed loop gain follows the close to the ideal case, like a 1 over beta gain, right? Like that. Right? So this is something that you have to understand the where the frequency that the feedback becomes effective, right? Out of that frequency, this critical point, the negative feedback becomes, the feedback property disappears, so the gain just follows the typical original amplifier gain. Why? Because this feedback, the negative subtracting term becomes negligible after this frequency, right? So it just becomes like open loop gain. You just follow the open loop gain response, right? Now the question is, what would happen if we just increase the bandwidth by the feedback, but our DC gain, the passband gain, has been reduced? So on the left hand side, let's say the gain is original 100 and the bandwidth is 10 megahertz, right? In that case, for the input signal square waveform, since it is passing through this one-stage amplifier, your output response will be like this, very distorted, very slow, because your bandwidth, signal bandwidth, is only limited to 100 at 10 megahertz. But what if you just cascade the low pass band gain, which is 10, but the larger bandwidth, you just cascade smaller gain stage, but the larger bandwidth, like 100 megahertz, like kind of a cascade those two amplifier, then you get the overall passband gain would be 100, same as that. But the bandwidth is like close to 100 megahertz compared to 10 megahertz. So output response will be pretty sharp, right? So you will follow the input scale waveform more faithfully. You just follow the input. So as you can see on those two examples, having lower passband gain is not a problem, right? Because the lower gain can be overcome by the cascading stages. But the having smaller bandwidth, we cannot overcome just cascading smaller bandwidth amplifier. You get the lower bandwidth still. But if you start with a high bandwidth amplifier like this and then cascade those as you want, then you can get the very fast amplifier, right? This is the benefit of having a bandwidth extension out of the negative feedback.